Okay, good morning everyone, and welcome to the 2016 Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its cooperating society are proud to present Dr. Edward Guinan. Ed is a professor of astronomy and astrophysics at Villanova University, located just outside Philadelphia, Pennsylvania. He holds a bachelor's degree in physics from Villanova University and a PhD in astronomy from the University of Pennsylvania in Philadelphia. Ed's research interests focus on binary star systems, black holes, the evolution of the sun and sun-like stars, pulsating stars, the search for exoplanets, and the suitability of exoplanets for life. He is a guest investigator on a number of NASA astronomy space observatories, including the Hubble and Spitzer space telescopes, the Chandra X-ray Observatory, and the Kepler Planet Quest mission. He also sits on numerous committees for the NASA and other astronomical and space exploration groups, and is a strong proponent of science education in developing countries such as in Africa, Asia, Central and South America, the Middle East, and North Korea. Over the span of his career, Ed has accumulated a long list of achievements. For example, in 1968, Ed and two colleagues were the first to discover the system of rings that surrounded the planet Neptune. In the 1970s, he was involved in building Iran's first high-powered telescope. Ed is also an advocate for space travel and is a founding member of the Star Voyager project for human interstellar exploration. And finally, Ed participated in the vote of the International Astronomical Union to change the status of Pluto from a planet to a dwarf planet. Today, we are very fortunate to receive Ed, who will discuss the properties of stars and planets that appear necessary for life to form, new missions and techniques being developed to detect signatures of life on exoplanets, and finally, the feasibility of interstellar missions to reach those planets. So please join me in welcoming Dr. Edward Guinan.
Thank you very much. As you see, I might have some problems getting back in the United States with visiting North Korea, Iran, Syria. And also I have problems with school children demoting Pluto to relegating it to a dwarf planet. I got hate mail from, actually a death threat from the third grade students. So, yeah. So sometimes you have to watch out. So today I'm very happy to be here. I was here in 1992 when we had a meeting in Calgary, or 93, for astronomy. University of Calgary hosted it, and we made a trip up here to visit the museum. And it's like an iceberg. We only got to the lobby part in the showings, but seeing the whole rest of the museum is like an iceberg. 90% of it is all the research labs, so it's very nice to get behind the scenes with Francois. So today I'll be talking about mainly searching. I don't search for planets. I do the stars. I actually look at the stars that these planets host to try to figure out whether something can live on that planet. So I found only in all this there was 6,000 exoplanets. Terminology: exoplanet is a planet outside the solar system. So an habitable zone, you're going to see that come up, is where liquid water can be. In our own solar system, it's about where we are, a little bit inside. We're near the hot part. We're not going to be in the habitable zone in about a 500 million years. We're no longer in it, and that means we'll start to lose our water, our ecosystem will start to go. I often tell people like in a few weeks that's going to happen, but it's about a 500 million years. And that goes out to about Mars, is where it is in our own solar system. So let me start to figure out this. This is the forward. So that's the talking points. This is like a smorgasbord. There's going to be things. I'll show some slides, but I might skip over them. I didn't put them all at the end. I edited this last night. It was too long, but I decided just to leave them in and skip, because you might see something in there you want me to go back for. So I'm going to introduce you to planet hunting. It actually started much earlier than you think. People began to think about planets 3,000 years ago, exoplanets. I have a program called Sun in Time, and that's a program where I don't need glasses, do I? I thought I'd be reading off my own computer. It's a program where we're studying the sun over its ages and how it changed and how it affected the planets. And we have a thing called red dwarfs. These are little stars, 1/10 the size of the sun, but they occupy 75% of all stars. talking about nearby planets and stars, pick out a few of them that could be habitable. See, these are ones that might be the best choices for life. And then at the end, sort of speculation on going there, interstellar travel, what might be the best ones to visit. So this is, if those who are students who like to do this, citizen science, you can go on here at this website and you can hunt planets. They give you material that you can look for telltale clues of the possibility of a habitable planet from eclipses, from what's called a transit. So this is a brief summary, so it goes way back. Epicurus is more known for his eating and gluttony and things like that, but and you can see maybe this there, and this isn't exactly a great faculty meeting. Maybe it is in some places. It looked like it might be fun. But he said there's infinite worlds. This is 3,300 BC, both like and unlike our own world, and we must believe that all worlds, there might be living creatures and planets and other things that we see in this world. So he's one of the first people to consider life outside of the Earth. And more recently, it's Giordano Bruno in 1584, who actually was more scientific about it because they knew about stars. Stars were suns. And he was saying that quoting part of it, we see only the suns because they are the largest bodies and more luminous, but their planets remained invisible. So he believed, not many people at that time believed that these stars could have planets around them. He was, in a little bit later than that, 1592, he was burned at the stake, not for saying that, for being a heretic, for saying other things that weren't complimentary to the Pope. The other person, his mother was accused of being a witch, which isn't maybe she was, but she wasn't very nice. And then you have even Immanuel Kant, who's also taking the same tack about that many stars could have planets like our own. Even Isaac Newton, people in that era were, once they realized that stars were suns and not little holes in our celestial sphere, began to speculate on planets around them. It wasn't until 1995, there was 1992, there was the planets discovered around a pulsar, but 1995 is when this all began. There were no planets outside the solar system, well, that were known. There's many billions of them. And these two groups, Mayor and Quilez and Marcy and Butler, Marcy Butler down here, found radial velocity. They found motions of a star. A star was moving to and fro, producing what's called a Doppler effect. And that was a signature. This is how it works. So this is the star. And the planet pulls the star slightly. You can't see that planet, but you see that star moving forward and backwards periodically. That produces a red shift, a shift in the wavelength toward the red, and when it's going away from you, a blue shift. So it's like this. So this is the orbit of the planet. You can't see this guy, but you do see the star being pulled by gravity toward you, blue shift, or away from you, red shift. And if it's periodic, there's got to be a body around there. So that's where it began. This is the curve. This is a star called 51 Pegasi. It's the first star to have this found, and now there are 400. And this is a plot of its time. The period of the star is, you can sort of hear, it's about 4.5 days. And this is the curve. Up is positive. It's when it's moving away from you. And the bottom part is moving toward you. So it would be like this up there. Again, you cannot see the planet here, but it's pulling the star ever so slightly. Same thing is happening in our own solar system to the sun. The sun also has a wobble. And the other discoveries, so I'm going through this pretty fast. So there are 400 planets discovered using that method. Another one is to look for what's called transit eclipses. And this is when the star and planet are almost in the same line of sight, so that the planet goes in front of the star and produces an eclipse. It's a tiny eclipse. So you have the planet out here. This is a drop in light. Again, there's no light coming from this. And this, in our own solar system, this is only 1.2% if this were Jupiter. This is made up for Jupiter and the sun. The sun is about 10 times bigger than Jupiter. Earth is going to be much smaller. So what you get is a curve like that, or you get something schematically that looks like that. The depth of that eclipse, the depth of the drop, is telling you what the radius of the star is, because it's an area, the area covered. So it's going to be down here, the planet area, the planet radius over the planet, or the star's radius. Is the reason there's a half in here is because it's pi r squared. So the area covered is going to have a square in there. So you take the square root. Very simple. It's not so simple when you actually do this for real, taking in all the accounts. So this is an example then of what would happen in our own solar system. Jupiter is 1/10 the size of the sun in diameter. So it produces, when you do that radius, if you put 1 over 100 and you square it, you'll get about 1.2%. So if Jupiter went in front of the sun, you get a 2%, 1% drop. You can actually see that from the ground. You could use ground-based photometry, and you could measure it. It's hard. You can do 1/2 to 1% precision because the atmosphere and clouds kind of make it difficult to measure high precisions. Neptune is 4 times the radius of the Earth, and that produces a signal that would be very, very hard to find on Earth from Earth-based telescopes, 0.15%. And Earth is the red mark, impossible to do from the ground. It produces only 1/100th of a percent, or 0.1 part in 100,000 signal as it moved in front, because it's tiny. You can just barely see the Earth there. So when that moves in front, it produces a tiny signal that can't be detected any instrumentation from the ground. So what happened is that you go into space. So when you're in space, you're above the atmosphere, above clouds, haze, turbulence. And there are several missions, Corot, a French mission, and Kepler, a US mission. That's actually, it's I think Canada has a piece of this. And what this telescope does is stares. It orbits the Earth, or used to orbit the Earth. It's moved away. And it points in the same direction for 4 years. So it has a big field of view. Actually, you can see like a field of view that's like 20 moons by 20 moons, which contains hundreds of thousands of stars, and it just stares at them and measures their brightnesses. And what you're looking for is a transit event. So this is the Kepler itself. Here's the field of view. It's in the constellation Cygnus. Those little bars are the detectors, the CCDs, like on your cameras, except they're much more sensitive. And this thing points with a precision of 1/10 of an arc second in that direction. It stares. Every 3 months they roll it, but it still points there. So 4 continuous years of data monitoring light to the precision where you could detect an Earth, and they have detected an several Earth-sized planets. If you want to see more what's happened, this is their website, Kepler, NASA.gov, and has so far gotten 6,000 what are called possible candidate planets, and then 2,000 confirmed planets. So things look like this. So this is the transits I was telling you. Here's a big star. Here's a big planet. So this is 1% deep. This is like something close to the Earth, where you can barely see it. It produces only a 100th of a percent, so 1 part in 10,000. So it's able to sample, and you need the time because you have to go back and repeat to make sure it's a planet and not a spot. I mean, stars have spots. So this, you can get a dip like this from a spot, but it won't happen periodically. So the orbit of the planet is the clue. The periodicity is what gives you the fact that it's a planet. And here's just a few examples. There's 2,000 of these. So I just picked out one I thought was cool. This is Kepler 11. How they name these, Kepler's the instrument that discovered it. So this is Kepler 11. It's their 11th object. The star itself is A, so that's what they call the star. And all the planets or anything else, any other bodies are given B, C, D, E. In our solar system, the sun would be A, Sol A, and Mercury would be not called that; it would be Sol B, and then we would be the C in that system. What you're seeing here is a record of time, at 100 days, and this is the signal. This is 0.99. So this is tiny here. This 1% is way down here someplace. So this is a signal we're able to pull out. these dips in here, these dips, are all due to planets going across the face of the star. This star has 6 planets that are all in the same plane that go across and make eclipses. So I just labeled them. This guy here is the same one, so it has, you can get its period. Here it's periodic. This one here is a bigger one and longer period. You have, so sometimes they add up. They all get in, like this guy. See, there's 3. You get a deep one. So you have periods all sometimes adding, sometimes not adding, that go across there, and you get a signal like this. And what they do is they analyze this using a technique to pull out the periods. And because they got to be periodic. And the lake curves are up in there, and some of these are tiny. One is like nearly the size of the Earth and produces only a tiny signal. I think it's this one here. And there's also noise in here too. Stars have spots and things like that, so there's some, but the noise is usually random. So that's a neat system. It's called, and none of these planets you would want to live on. So this is a comparison. They're all in the same plane, and it's not unusual because the sun and our other planets, except maybe, well, Pluto's no longer a planet, thanks to me, but I know, sis, okay, and she's making faces at me. I didn't do it alone, come on, it wasn't just me. But they all orbit in the same plane, so much like our own solar system. So if you looked at our own solar system from the right place, you would actually see transits too. Not all the planets would be there. So this is the scale. Notice that a Kepler 11 system, you can think some of these planets are 2 or 3 times the size of the Earth, which is okay. They're called SuperEarths because they're just bigger, but they're still terrestrial. But notice here they're going to be hot. They're all inside of Venus's orbit. The habitable zone is out here. Earth is here in this picture. So these are hot planets, places you wouldn't want to live on, especially that one that's really close, because it's 2,000 degrees on that planet's surface. So just give you an example that there's many multiple planetary systems. In fact, almost half. This is one you don't want to think much about. This is a scary one, and it came out of the Kepler mission. I'm putting it in here. This is a whole talk on its own, because these things have gotten news. And they're called rogue planets, if you want to call them that, or nomad planets. These are planets without a star. And the Kepler mission found these, actually only 2 have actually been found, but when they analyzed those multiple planet systems, they found out that about 1/3 of them were not stable, that the planets were either going to be kicked into the star or ejected. And so the analysis, our own solar system, we have about 2 billion years of stability, probably longer. So you have to watch out. Solar systems aren't always stable. Ours is. Ours was not stable early, and we may have lost a few planets. And there were collisions that took place and things like that. Things have calmed down. But in the Kepler data, there's evidence that about 1/3 of the planet systems they found will not keep all the planets. So this is either called rejected, if you want to look at it that way, or ejected from their host stars. And they're out there. And these are planets free-floating in space. You can't see them. They're faint. In fact, they're almost invisible. And this is the number that's quite scary, is 10 to 25% of the Kepler data, when they did the analysis, show that they have unstable solar systems and that things are going to either get, you hope they get thrown into the star, but half of them actually will be thrown out. It may have happened in our own solar system early on. Hopefully it's finished. And the number is kind of high. I mean, and when you scale this up to how many stars there are in our galaxy, there's 25 to 50 billion of them. And you won't see them until they're right on top of you. And these could explain some of the things that happened in our own solar system. So if one of these just came near our solar system, it would destabilize it, which is come back to later on. Hope nothing happens like that. There could be one sitting out there heading toward us. We'd eventually see it a couple years before it came in, because they do emit infrared or heat energy, and there are satellites that can monitor that. I talked about 2 methods. The transit method, because it got like 90% of the planets were found by that method using Kepler. There's a few planets that have been imaged. Actually, there's images of them. You have to use special methods because the star is so bright, it overwhelms the planet's light by a factor of sometimes 1,000,000 to 1,000,000,000 to 1. So they use different methods. Sometimes they use they block the star out. Like this case, the star is here, but they put a coronagraph, they put a shield here that blocks the light of the star out, revealing the planet. If you saw this with the star, you would never, the glare of the star would go out there. And some cases, they use adaptive optics, telescopes with mirrors that bend because the atmosphere smears the light. So this case, they're removing the star using adaptive optics methods, and there's another planet. So these are just examples of imaging. These planets are big. They're not Earth-size, because Earth-sized planets you couldn't see yet, but they're like the size of Jupiter or bigger. Even in this case, the middle one, Beta Pictoris, they even see the whole center part's blocked away. That's the star. You can't see it because they eliminated it. And it shows a protoplanetary disk. See that disk running along there? I should find the pointer. I can't reach that high. Yeah, it's here, isn't it? I'll figure it out before the end of the talk. And I'll see if it works. Here we go. Yeah, this is a disk. This is planets forming. It's a very young star. So our solar system was like that 4 billion, 5 billion years ago, and the planets formed inside of here. They blocked out the star, and in here, I didn't show it, in here, in fact, it's right here, they found a planet. Actually, there's a planet, a forming planet. So these are, you can image. Quality of things are getting high enough, telescopes are getting better and bigger, that you can actually start to image some of the stars. The fourth method, this method has only produced 20 exoplanets, and this uses what's called gravitational lensing. Here's a star, here's a distant star, here's a body going in front of it. Normally the light from this you're down in here, the light from the star squiggles out like this, and you get one beam. What happens is that this bends the light. A beam that would go out here and never reach our eye will be bent around like a lens. And as this body moves in front of the star, it amplifies it, this is brightness, causing what is called a microlens or gravitational lensing. And that's been done for about 50 stars. Sometimes, in a few cases, they find two signatures. The star goes by, it bends the light around so you get more of it, you get this amplification. But then there's a little twitch here, and this is due to a planet. So they were able to detect planets. This is the planet's gravity bending the light, making a tiny lens, directing that light toward Earth, and you get a little brightening. Here's a blow-up of it. So they've gotten 20 of these. It only happens once, because this planet's going to move away, or the star's going to move away, and it will never come back again. You don't know the period. You don't know much about it except how massive it is. So here's a case where you have this event going on, and there's a whole array of telescopes that when this happens with a star, they tune in to see if they see this extra blip due to a hosted planet. In all the cases, they've only found evidence of one free-floating planet. Every planet has been connected with a star. But again, this clues the system in. When this is going on, everybody jumps in, because you could have a cloudy day and night and miss that. So they all jump in and do coordinated observations. So only one case have they seen a planet, or would be a rogue planet, happen. So this is, there's a few more methods, but I've taken you through the methods. Most of the data now comes from Kepler, from transits, even though they're rare. And when you look at hundreds of thousands of stars, you're going to find them. Now I'm going to take you through the census, just some results quickly. Let's see this hand. This is a plot of number of detections, so it goes up to 800. This is time, and here's the first one. So there was a pulsar detection out in here, but so you see this is by radial velocity is red, and they're doing quite well, but then Kepler comes into play right about here, reducing their data, and these green mark here has to do with the Kepler data being reduced. Sometimes it takes a couple years to reduce the data and figure out that they're planets. The reason it's gone down is that Kepler lost one of its gyros, so it couldn't keep pointing in that position. They repositioned it. They used novel kind of celestial mechanics to have it continue on, but now it has to point at different directions of the sky. It's called K2, kind of after the mountain, and also you have to think of clever names when you're trying to extend a broken satellite. And they did. They got about $10 million to continue doing this, and they're still finding planets, but not as many. And this gives you most of this is period, so in terms of the Earth's sun, we're in here someplace. We're right mass of Jupiter, so we're down in there somewhere. Would be 300, be the Earth. So most of the long period ones are done by radial velocity. The Kepler data is kind of tuned into short period planets which have smaller orbits, because they roll it every 90 days, and then you lose it. The stars fall in different parts of the detector. The planets form on different parts of the detectors, and it screws them up. So normally they get short period because they're easier to detect, and the radial velocity is mostly long period. Still being done. Radial velocities are being done with Keck. Biggest telescopes in the world have to do it. This is the summary. Confirmed. This changes every day. I checked last night, but I was too tired to put in. I think there's another planet. I think it's 66, but I didn't have time to change the slide. So there are 1964 of them, and there might be even 2,000 of what are called confirmed exoplanets. By Doppler, that's the radial velocity, motion using redshifts and blue shifts. That's the transit method. Most of these are transit. Of those, they're not each star. There are 484 multiple systems, 2 or more planets around. I showed you one with 6 planets. So there are several of those. Not several, there are dozens of them. Exoplanet candidates. These are ones waiting to be tested, because you can't tell. What Kepler gives you is a blip, and you don't, a dip, and you can't tell the properties. You have to confirm it. So there's almost 4,700 of those waiting. In the past, when they had these exoplanet candidates, about 90% made it into the confirmed category. So you're going to have maybe 80 to 90% of those turning out to be planetary systems orbiting that many stars. So this is mostly from Kepler again. There are unconfirmed. Corot is a French mission, and it has about 186 waiting to be confirmed. Confirming means you take extra observations. Potentially habitable. Of all these, most of these planets are things you wouldn't want to live on because they're close to the star, or they're big, or they're gaseous. They're like Jupiter, which is a big gaseous planet. There are only a handful, well, not a handful anymore, there are 32 of them that are called potentially habitable exoplanets. These are guys that are up to 5 times the mass of the Earth, 1 to 5 times. One is a Mars-sized planet, but that's the general range. And they are in the zone distance from the star where you'll have liquid water if they're Earth-like. So they'll have a hard surface. They'll be called terrestrial. It means you can walk on them, unlike Jupiter, which is gas. And they'll have kind of a climate in the range of what the Earth would be if they're like the Earth, if they have an atmosphere and greenhouse effect and things like that. If the Earth didn't have a greenhouse effect, for example, the Earth would be frozen. So you have to build in assumptions when you're doing that. So none of these are what are called Earth 2. Everybody's looking for Earth 2.0. That has not been found. I'm looking forward to. Everybody is. They're very rare, probably. Have one that's the same age, same properties. But some of these are getting closer. I'm going to show you some examples. This is when you scale this up, and that's what Kepler was able to do. It was able to tell you how fraction of the stars they looked at had planets, and in the habitable zone. And it turns out that a lot do. Because Kepler misses, most of the transits don't happen. The planet moves above or below. It has to be almost in your line of sight, exactly in your plane. So you miss most of the planets. So they take that into account, and they estimate how many there are. And they estimate it, because there's a lot of stars in our galaxy, 50 to 100 billion planets in our galaxy. And this is red dwarfs is what I work on too. These are small stars. They make up 70% of all stars. These have also very high numbers. Something like 25% of these stars have planets in the habitable zone, Earth-sized planets. Nomad planets, the scary ones, is 25 to 50 billion. But of all these, we only know one planet so far with life. I think you know its name. And maybe something might happen on Mars. We might find primitive life on Europa. But that's it so far. And that's probably going to stay this way for a long time. And if you wanted to check this out further, you can go. It's fun to go to this catalog. You can look up all the properties. I have fun. I read it just for fun. see what's new. I'm a nerd. It's something. I watch television, watch Star Trek, and I look into this catalog. I say, yeah, there's a new one coming along. And this is how it's changed. They have that catalog, gives you this photo gallery. And none one knows what they look like. This is a little artist, They make them different, but I mean, who knows? And so in 2012, when this started, they have an index called to compare, it's called Similarity Index to Earth. If you were 1 here, you would be the Earth, or you would not be the Earth. You would have a mass, a temperature. You wouldn't know if it had water or not, but you would have almost the same radiative properties, the same energy from the sun, same mass, stuff like that. So in here, these are weird names. This is one of my favorites, though, Gliese 581. I do that guy. And these are actually, a lot of these, until Kepler came along, are pretty close. I mean, I think a light year's close. Light year, to me, is next door. You'll see what a light year is soon. It's a trillion kilometers, but to me, that's the nearby star. So they run across here, and this was what they got in this Earth Similarity Index. And there were, how many of them? 9 of them. Going forward, I just looked it up in January and April. There are 32 of them. Now, a lot of these are too far away. If you wanted to travel, all the Kepler stars are faint. So most of the things that labeled Kepler, even though they might be near, this guy has a very similar size and heat or temperature to what the Earth would have if this were the Earth. But it's very far away. It's hundreds of light years away. So when you skip over here and find stars like this is within 20 light years, which is I would call neighborhood stars. So scanning across here, this has become larger, but what's happened is that it's being heavily skewed with stars that are far away that you wouldn't have a chance to get to. Again, it's called the PHL Planetary Habitability Laboratory. So people like to have these websites that they make them up. Here's a new one where we're looking at that one too. We don't look at this planet. I look at the star that planet inhabits. We have 2 programs, quickies. My science part of this is I have a program called the Sun and Time. That clock has a problem. It moves, but it always stays around 3 o'clock. And this is a comprehensive study of the sun, but using stars like the sun. The sun's a G2 star, so it uses what are called solar proxies. You take stars like the sun in a very young cluster, like there's a cluster called the Pleiades that you see in the sky here. That's 100 million years old. We look at the stars there, and that would be taken as the sun 4.5 billion years ago. So we have a whole group of these clusters and stars with ages like the sun-type star. And I have time on Hubble Space Telescope, Spitzer X-ray telescopes to study these stars. And what we're looking at is our relationship. So this has been funded for a long time, since 1990, not continuously. And I'm pressing the wrong button. This is the only science. What happens in here is, this is period of rotation. That's how fast the star spins. Here's the sun. It's up here. The sun's age is 4.5 billion years. So what happens, if you look at this diagram, is that the young sun, back in here in the Hyades, is these stars, when they're 500 million years old, are spending 7 days. A very young star spending 2 days. So this is the history of the sun. These are different stars acting as proxies for the sun. So, and the reason this is important is that we use this to get ages. We calibrated this, and if you find a star, if you give me a G star's rotation period, say it is 8 days, I can tell you that that star is 700 million years old, like Kreskin. because it's here, it's calibrated. These stars right here are that. And it's very useful because it's very hard to get an age of a star. And if that star has planets, I can then tell you these planets are very young or very old or older than us by just knowing their rotation. This is a nice law. And Alpha Centauri, which is the next nearest star, is 5 billion years old. So here's another thing that comes in, and just quick. And one of the nasty things that stars do, what the sun did even, is that they emit a lot of X-rays and far ultraviolet radiation, which can ruin the atmosphere of the planet, of the hosted planet. And when the star is spinning this fast, it has a dynamo, produces strong magnetic fields, star spots that are hundreds of times, cover hundreds of times more area than on the sun today. And they produce copious amounts of X-rays. That LX is X-ray emission. So when the sun was young, this is the sun, EK Draconis is a stand-in, it was producing this is a log scale, here's the sun today, about a third magnitudes, that's 1,000 times more X-rays. So the sun, 4.5 billion years ago, was producing 1,000 times more X-ray, and we were getting it. So this is what this diagram shows. It shows you the history, or can be used to show you the history of the sun back in time. That's why we call it the sun in time. We've done this for ultraviolet. We've done this for infrared. We have many, and we use these to analyze the early solar system. Like what happened to Venus, why we're here, why Mars doesn't have an atmosphere. I'm going to show you one result. Why Venus has problems, why Earth made it. Earth made it through because, I can tell you why now, it has a strong magnetic field that actually protected it from the nasty things. The sun was a bad star. It was, in fact, life couldn't have started the first 500 million years of the sun, blowing up, flares, because we see stars that are like the sun, the same mass, but now they're young, and they're doing bad things. Flares every day, 10 of them, big enough to wipe us out. So the sun has calmed down, because it's a middle-aged star now. People calm down, stars calm down. and so it's not as, oh, you noticed that. I'm noticing it too. I think I'm down in here too. I'm in here. I hope I last to here. And in my youth, I don't know if I did that much. I think I blew my youth. I should have been more flaring. So that's what we do. So I'll show you. This is then, I didn't want to put too much, I don't want to go too much into that. That data was taken with Hubble, with X-ray satellites and all. That's how stuff. This is a plot of, this is solar flux. This is flux received at different ages. This gigayears is 1 billion years, so that's 4 billion years. The sun is 4.5. So there's the sun. Everything has been normalized to the sun. The log of 1 is 0. So I'm sorry, it's all, but I couldn't plot this on a normal scale because it would be a factor of 1,000. So logs make it easier to look at. This, first of all, this is the luminosity of the sun. So this is the sun getting bigger, getting more luminous with time. It's increasing about 7% in its luminosity. So when it was a baby star, it was dimmer than the sun today, 70% of what it. So over time, and we wonder, there's a thing called the dim sun paradox. Sounds like Chinese restaurant on Sunday mornings, but I had to say the faint sun paradox, easier for me to say. But there was a problem with if the sun was 70%, Earth should have frozen over. Earth should have been ice all the way up to about here. And it was Carl Sagan who actually figured out why, is that the Earth in its early years had stronger greenhouse gases than it has today. Methane was one of them and had more carbon dioxide. So that's why the Earth the dim sun paradox is no longer a paradox, it's understood. But what happens a little bit here is that this goes up 7%, and when you get into about 1 billion years, the sun would be about 1% more luminosity, and we're no longer in the habitable zone. The Earth is on the very edge of it, and that's the case when we have what's called a wet greenhouse or a runaway greenhouse effect. It gets warm enough, but it's happening faster because of people. I mean, the sun is eventually going to cut in two, and about 1 billion years from now, the Earth will be too hot for most of us. I mean, rats, probably roaches, things like that might enjoy climate. And in the very distant future, the sun becomes a red giant and goes way up in here. That is, the sun expands out, and we're inside of it. That will make a lot of my friends who are solar physicists really happy, because they always want to see what's inside the sun. And if they wait 5 billion years, they'll get to see it. So this is the result of our study. This is used in a lot of papers, and we published this, and it has to be revised because we have more numbers. We have stars out here now, and we have stars filling in this part. So this is hard X-rays, soft X-rays, far ultraviolet. All these things do things to our atmosphere. Far ultraviolet breaks water up. It photolyzes water. The water molecule H2O is broken up into hydrogen, oxygen, and escapes. So all these things have mostly negative, but some positive effects. They affect the evolution, like they can produce formaldehyde, which is carcinogenic, but we need formaldehyde for ribose, for producing more complex molecules. So there's a whole story where you do the photochemistry of the sun and the planets using this data to do it. And some of it's good. This is the one result I'll show. Mars, there's evidence now that Mars has frozen water, had liquid water for the first billion years of its life. There are lakes, dried up lakes on Mars. There's rivers, dry rivers, and there's actually ice. And if you go into the Martian soil, there's permafrost. So Mars once had liquid water, and it was a happy planet. It had a big greenhouse effect, happy, maybe even life for the first billion years. So it was formed 4.5 billion years. So about 3.5 billion years ago, this is what was happening. Mars had a magnetic field. It had an iron core like we had, liquid, and produced a field. In fact, this is the Earth's field. I just stuck Mars in front of it. I don't have a lot of money to make new artistic rendition. So this is what happens in here is the solar wind gets deflected around here, and Mars was happy. And further away from the sun, but it gets 1/2 as much radiation as we did. But it was protected from the flares and the nasty plasma that the sun puts out. But what happened is that Mars is a smaller planet. Its heat capacity is lower. The core cooled, and when it cooled, it solidified, and its magnetic field cut off about 3.5 billion years ago. So then things could come in, and plasma could come in, and started to sweep away, broke the water molecules up into H and to O's. The O's stayed behind, but the hydrogens escaped, and were swept away by the wind. I'll show that last one. So this is Mars. This is what happened then. This is a bad picture. Here's the sun. The sun is very far away. So about that time, the X-ray and UV radiation was coming in. It was still strong. The sun was still going pretty well. It wasn't 1,000 times stronger, but it was 100 times stronger than today. And Mars was no longer protected from this shield. So what happened is that the wind and the plasma, the ultraviolet X-rays, broke molecules up like hydrogen, water, and the hydrogen escaped into space. Oxygen went into the surface, and this is what happened. It cooled down. Mars rapidly cooled down into a frozen, kind of a desolate planet like it is today. In our model, it doesn't all go away. It got cold so fast that ice formed, and it left behind about 1/4 of the water in the form of ice. And that's what we're finding. That was a result published in 2003. We didn't know, and it's working out that it is turning out that way. So Mars has lots of oxygen on its surface. That oxygen came from the water. So this is why we're here, is that it's because we're finding out in the study, in my collaborators who do magnetic fields, the sun is not that close. This is the Earth's field, is that when you look at this, why we're here is that the Earth had a magnetic field through time. Earth had a magnetic field from at least 4 billion years ago to the present. Sometimes it cuts off, but it's been around, and it's pretty strong. And so it always has this area here is the magnetosphere. This is the sun's radiation hitting it and being deflected around. So the Earth, is probably not a coincidence that Venus doesn't have a field, Mars doesn't have a field, Earth and Mercury doesn't have a field. Mercury has its own problems, though. So it's the only terrestrial planet in our solar system with a magnetic field, and it's the only one with life. So is it a coincidence or is it not? It's probably the reason that we have complex life is because the Earth's atmosphere was not swept away. Mars has other problems. It's a smaller planet, so its atmosphere is easier to rip off. But on the other hand, it's further away from the sun, so it's not as in a dangerous position. But that's our common feeling now, is that these exoplanets better have magnetic fields, because when the stars are young, they will sweep away, eliminate the planet's atmosphere, like what happened on Mercury. Venus got its original atmosphere taken out, but then volcanoes produced carbon dioxide. Our other program is called Living with a Red Dwarf. We had this as this is not our original. You have to get money in the United States from government, from panels, you have to have catchy titles like The Sun in Time. I don't have that copyright, someone else copyright. I stole it from a book. I went to a conference called The Sun in Time. That's a good title for a proposal. Mine was the dynamo action and something or other, magneto energy of the sun. When I made it The Sun in Time, yeah, it's simple. So I called this one Living with a Red Dwarf because there's a study called Living with Our Star, so I called it Red Dwarf. And this wasn't the original one. We have a website. The one I wanted to use was this, but NASA frowned on having their logo on the bed of the 7 dwarfs. So, I don't know. Moving on. So this program does almost the same thing. It just is a copy of the Sun program, except with smaller stars. Why red dwarfs? Because there's 75% of stars are red dwarfs. The nearest star to the Sun is a red dwarf, Proxima Centauri. So there's so many of them that you want to see if they can support habitable planets. And so we went through the same thing, X-rays, ultraviolet, all those satellites, flare studies, to see what the game is, whether they could host habitable planets. We had a lot of trouble getting time or getting money for this program early on because in 2004 there were no planets found around a red dwarf. And it wasn't until 2005 or 6 that they were starting to find them. So we said, why there's no planets? The reason they thought they wouldn't be planets is because red dwarfs are small. They have 1/2 to 1/10 the mass of the sun. And planets are forming from the garbage, from the residue left over from a star form. Stars form, they collapse. The center part becomes the star, which is 90% of the mass, 95%. And the stuff left over is where the planets form. They figured that there wasn't enough stuff left over to form planets because they started out with a mass of 1/10 of a sun mass. So there's not much there that you can form a planet with. And it's true. Red dwarfs favor forming Earth-sized planets. They have a trouble forming a Jupiter-sized planet. But I don't care about a Jupiter-sized planet. I'd rather live on a Earth-sized planet. So they are the most common. 25% of red dwarfs have Earth-sized planets in their habitable zones. So their habitable zones is going to be going to be close to the stars. This is being taped. Close to the site. Once dropped and I used a word beginning with an S. There's children here. It was shucks. So what we have here then is that this program is continuing, and I keep thinking I'm not used to dealing with. So the reason you do this is a graph of the different types of stars. Sun's a G star. So 75% of these guys are red dwarfs. So they're the most common stars. This is a picture of the Sun, and these are red dwarfs. Some of them can be quite tiny, almost the size. Jupiter's about that size. This is the spectral classification. These are their properties, just quickly, masses. One mass is the Sun, 0.47, 0.2. Proxima Centauri is like in here someplace, if you're familiar with that. But they have low luminosities. This is how much energy they put out. So this is a problem that you have to live close to the star to be warm. Like this star, you have to live right on top of it because it's very, very faint. So they have what are called small habitable zones. One of the positive things of red dwarfs is that they live forever, and I mean forever, 1 trillion years. This is the Sun. The Sun's doing fine. This is 0 when it was born. This is now. The Sun's getting brighter, more luminous, but 7%. But then when it gets to about 9 billion years, it goes up and becomes a red giant. we kind of die in here. Red dwarfs don't change. Their luminosities, because they burn their nuclear fuel at such low rates, they stay basically the same. So their habitable zones are fixed. The climates of planets around them are fixed. Earth's climate is getting warmer because of the sun getting brighter, more luminous. And in this time, right in here, is just this 10% increase is enough to trigger this runaway greenhouse effect. Why? I have to stop doing that. These are habitable zones. By the end of the talk, I'll have that figured out. My computer is, I'm used to giving this from my own computer. These are the habitable zones for our own solar system. Earth is at 1 AU, astronomical unit. Okay, it's distance that the Earth is from the sun, about 150 million kilometers. And so these are the outer. If you're generous, you could go out, have a planet at 2 AU. If you had a big greenhouse effect, if I moved Venus from here to here, Venus would be all right. I don't think it would like being moved, but it would have, because it has an enormous greenhouse effect. So this is the habitable zone for a solar star, and Earth is right on the border of being too hot. The inner is 0.8. That's really rough. You have to have. If I put Mars there, it would be all right. Put Mars 0.8 AU is 80% in. Mars might work there for a little while. K stars are intermediate. They have a mass of about 80%. The sun. Their habitable zones are smaller, so you could have life, water inside out to about 1 AU or so, and into about 0.5 AU. So, and M stars, though, look how close you have to be. I can't even draw it. The Earth equivalent position, if I put the Earth around one of these stars, it'd have to be 14%. It would be only like 10 million miles from the host star. So it would be very close, and that can cause some problems. That's the result. That's same results. M stars now, as they age, their period gets longer, and their X-rays, as they are young, their X-rays are strong and decrease with time. So the bottom line here is that you need, as in the case, even more so, you need strong magnetic fields, because in some cases you are almost this close to the host star. I mean, this is made, you would be about, this planet would be out there. So you have to be warm enough, you have to be close to the host star, but you better be protected with strong magnetic fields, because there's going to be a lot of plasmas. These stars flare and have all kinds of emissions. So there's, on the downside, there is a downside. Being so close, you have to have a very strong magnetic field to protect it, especially when they're young and very active. And there's a picture of my only movie. So this is the sun, or it could be a G star, a young star, an M dwarf. And so they have these ejections called coronal mass ejections and flares. That stuff flies out, and that's nice. That magnetic field is preventing the stuff from going right in. It does come back and hits Canada, northern Canada. There's the and I have to stop the loop. Hits more Greenland than Canada, northern Canada anyway. So it comes in about 100 kilometers up. It interacts with the atmosphere, and you have beautiful aurora. So it doesn't get to the equator very often. So here we'll watch it. Coming right in. Here's Canada right in there someplace. Okay, last part is, the second to last part, if I get time to do what time do I have? Ooh, I'm out of time. So these are the nearby stars, the Sun, Alpha Centauri's this band. So these are the names of the nearest stars. I'll just take you through. Everybody likes Alpha Centauri, and maybe you saw Avatar. Avatar was one of the moons of one of the host stars. Alpha Centauri doesn't have a planet like that. It's a movie, but it is the nearest star. And it's only 4.9. Let's do it. I'm in Canada, so 9.9625 billion kilometers away. If it's in the U.S., I have to do miles, and so that's what a light year is. So it's very far, very nearby. It's a binary system. Alpha Centauri A, B, and Proxima is out here. We're here. We're in this direction. So this is the nearest star to us. pictures of it. They found a planet, not a nice planet. Alpha Centauri B is the cooler one, and B is the planet, little b, and it's 0.04 astronomically. It's right on top of the star. So you can imagine it's hot there, 1900 degrees Celsius, and it may not even exist. It may be an artifact of the analysis. Proxima Centauri, a red dwarf. I like that star. Its habitable zone is tiny, but no planets have been detected. We're still studying it because it is the nearest star and is a red dwarf. It is not, a binary. It's way distant from the other two. The next nearest star is with a planet. It's called Epsilon Eridani. This is the birthplace of Spock, supposedly. I question that, but because it doesn't make some sense. This star is very young. This star is a baby star. In fact, the planets are still forming on this guy. So this is a very young star. So if Vulcan were there, meaning 600 million years, it took 4 billion years. So I doubt that was a good choice for him. One of my favorites is Captain star. It's an old red dwarf. It's 12 light years away. The nearest old star. The interesting thing about this one is it's older than the sun, older than us by 5 billion years. So if life were there and could exist, could stay, it would be could be advanced life, like aliens, and who knows, or maybe they wipe themselves out. So this is a picture of Captain B, again, artist. It's called a SuperEarth, and this is compared to the Earth. The one that makes the most sense, if you wanted to have, you have to say, where can I go if we had to escape, would be this Gliese 581. And this contains 2 stars in the habitable zone. It's a red dwarf. And so it has many. This is the sun, drawn to scale. These are that system. And only these guys are far enough away that you could have D and G, C, are near enough or far enough that you could have it be habitable. So here's the Earth. We're way out here. This is an M dwarf. So to be warm, you have to be close to the star. So I just drew the one on top of the other. But they always question that you can't, when you get that close to a star, you get tidally locked, like our moon is. Our moon has the same face, the same section, same hemisphere faces us, and the dark side of the moon, you never see it. What happens with the moon is the moon is synchronous. It rotates at the same period that it orbits. So you always have the facing side. That would happen with a star, a planet orbiting an M star, a red dwarf. It'd be so close, the tidal pull would keep one hemisphere always illuminated, one hemisphere in the dark. In the 90s, people said that's not going to work. What will happen is that the atmosphere of the planet will freeze out on the dark side, and the lit side, the hot side, will be a barren desert. Well, that's this case here. But they did further calculations, and they showed if you had an atmosphere or an ocean, it would circulate. So this is the cold side, but as it happens, this would be like the Earth. This is the equator of the Earth. The equator gets most of the energy. Then you get circulation around to the North Pole. So here you would have, this would be the facing side, and you would have air rising, a low pressure. Here would be high pressure, and you have a circulation of the cold air coming around to the hot side, and the hot rising air coming around and falling down to the other side, keeping the temperature within reasonable bounds. I don't even have, you could have liquid water. I think I cut the temperatures out. No, there they are. It's not so bad. So it depends on your models. So it would be 20 degrees C. Not bad. Could be reasonable temperatures. You want to live on the dark side, though. You don't want to live on, because it's still, look at here. Here's the number. So if you lived over here, it would still be very hot. That's pretty bad. This is not Fahrenheit either. That is for the American audience, but that's pretty bad. Over here, not bad. In fact, that's today. I think it's a few days ago, it was 30 here. So you got used to that. It'd just be dark. So you do your farming. You could live on the border. That would work, except the winds would be strong here. So this is it wouldn't be like the Earth, but this would work. If it had oceans, you'd have circulation. So we showed, this is called a SuperEarth because it's 4 times bigger, more massive than the Earth, so I made this up. And you would probably be different structure. You'd have to be the Hulk. So you would 2.5 times the gravity, so your leg muscles would, I could break, my shirt would break off. And I, but my only reference to dinosaurs is coming up. So it would be difficult for certain life forms, like my cat, who's way overweight, to live on such a, he can get up. He's on a diet. I got him down 4 kilos. But he bites me now. So, and like a giraffe would have a problem probably, and this guy here would look at long neck and skinny legs. I think these would have a definite problem, right? I don't know. Maybe they would adjust. Future, you have looking for evidences of life. You want to get at the atmospheres of the planets. There's a mission that's planned, but it's been cut and then replanned, called TPF. It actually can take spectra of the planets. And you can see here, here's the spectrum of Venus is here. Big CO2 line, carbon dioxide, because it's 95% carbon dioxide. We have carbon dioxide too, but we don't have, but notice Earth has water bands, it has ozone bands, and it has methane bands, not showing here. Here's Mars. Again, not very interesting, very similar to Venus, missing, has very weak water bands. Mars does have some water, but not much. So what you would look for is maybe something like this. Evidences of life would be methane. So this is being done, but for the bigger ones, not for Earth-size, but for Jupiter-sized planets, because Earth-sized planets are not bright enough to take these spectra. So the end, I'll just, since we're out of time, should I go 5 minutes? Want to go to stars? Okay, if you're a Trekkie, then this is interplanetary travel. I figured there was only one. What is this thing? Crystalline entity. God, you guys are good. You're good. And you know the mother who killed a crystalline? I made a society I've called MACE, Mothers Against Crystalline Entities. It killed her son. She killed the crystalline entity. And then you have a variety of different Death Stars and so on. And this would be a battle, having the Star Trek attacking the Death Star. I was telling you before the talk about in the second movie, Star Trek, in the Star Wars movie, why did they make the Death Star had that same fatal design that you could fly in the top here and wipe it out after the first movie? Bigger Death Star. It was like double death, triple death. So what you want to do here is, what you can do here is, one of the ideas for going to stars, and I don't think going to stars with people is a good idea, but we're worried about rogue planets, things like that hitting the Earth or coming in. So you might want to think about having human beings in other places other than the Earth. So Charles Bowden is the director of NASA. He says it's a one-planet species will not last long, and you need a multi-planet species has a much better chance of survival, which is true. And we do have people off orbit. They're in the ISS, International Space Station, but if no one's on Earth, they're going to eventually run out of food. And there's a movie where that happened, where I think Earth got the plague or something, and they were the only people left. So Earth is the home. The only species, human beings. Okay, let's try it. You could have different types of catastrophes. So all your eggs in one basket. This happens. This is the way it is now. You could have things like an asteroid hit, and that's the KT boundary, maybe, kind of thing, except this is very bad. You could have a zombie outbreak. I've seen movies, Z World, to know where that happens. Everybody becomes a zombie. And the gamma ray burster is real. Global warming, either us or the sun. And, of course, nuclear war, the old standby, which wouldn't wipe us out, but it would just make life, the species would be set back. I worry about now a little bit, this wouldn't happen with a rogue planet, but a rogue planet could disrupt the stability of the solar system. So there are lots of catastrophes that having off-world species would work, and there's people who do this. Star Voyager, I belong to this group. There's a group called Lifeboat Foundation, Safeguarding Humanity, and this was Homo Spacians. I thought that had the best name. And this is for, you can join these. I actually am a member of this one, an honorary member. It's odd, though. And this one is, it doesn't look good in your Vita. Did I take it out? I think I left it. So now we have the space station. Yeah, that's going to work. That has like a dozen people on it, but for how long? The moon is okay. The moon has water from comets hitting it. So they found water on the moon. They shot a mission in there, a satellite built by undergraduates, which was El Cross, and it was taking pictures. And the last thing they did is they let it run into the moon. And what came out of here was steam. So they saw it has water there. The water probably came from impact of comets, not original. Moon bases, who knows, money-wise, 2025, I put a question mark in. Space elevators, making it cheaper to get things in orbit and out of, up into orbit using a kind of a leverage system. Humans on Mars, then, you can book tickets. I don't think that's going to work, though. Here, it's called Mars One. They sold 500,000 tickets, or people booked. Anybody booked for that? Nobody's going to admit that. So maybe you have Mars in 2075. Mars could be terraformed. I mean, it has water. It's frozen, and you could go from this to this, but it would take a long, long time. So what you would do on Mars is that you would make little areas where you could have water, nuclear generators, and have oxygen coming out and carbon dioxide, and build back a greenhouse effect and a habitat. This is it's called terraforming. This is kind of very, very costly. And so what you would normally do with Mars is just be underground and have little habitats in there. And the interstellar travel part, rockets aren't going to work. I'll take you through. The nearest star is Alpha Centauri, and it's 40 light years. It's 4 light years away. So if you were traveling at the fastest speed we're going from satellites, it would take 80,000 years to get there using a conventional mission. If you're going 10th of the speed of light, 44 years. So you need to get into near the speed of, above what we're doing now. And there's people who've been around doing this for 50 years. The Icarus Interstellar is, Branson owns a piece of that, so it's a concept thing. I belong to, look at that one. That's Uhura. That's my best night for attending one of these conferences, which sometimes have crazy people, because sometimes they're dressed up as Romulans or, or Vulcans, which isn't so bad. So I was her host. She came in on a walker. I mean, it was very sad to see my hero. Well, it was nothing. She's 82. She looks great. We already have interstellar missions. Voyager, which flew by a lot of the planets and launched in 1977, actually left the solar system. It crossed the boundary. Here's our sun. We have a thing called the heliosphere, heliopause, where this is interstellar. This is kind of controlled by the sun. And these two satellites, missions, have now crossed the boundary. One of them has crossed the boundary and is in interstellar space. It'll take 1 million years for them to get near to any planet. They're not directed at any planet. And how do you get there? One way would be nuclear fusion using tritium, which is one of the most rarest things you can get. But it's on the moon. You can harvest that and use your nuclear. You don't want to use these. These come out of nuclear reactors, but you don't want tritium's really bad. Very poisonous, but it's a very good propulsion. You avoid the first 3 steps in the nuclear bomb. So you just have tritium, and you make helium, comes out the back, and you get a lot of energy. You could use this device here that can get you 0.2. This is scale. This is 10 miles. So this harvest hydrogen and ions in space and compresses them, shoots them out the back, and you can get to a speed of 0.2. This is science fiction, but there's science in it. Just getting something this big and building it in space seems hard. Antimatter, matter. There goes your Star Trek. Antimatter. There is a beer. I went to a conference where they had these beers. They were real, and I drank the antimatter beer. Okay, so then there could be concept where these produce gamma rays. So if you're in one of these ships, you want to live way up here. because you don't want those gamma rays to get you. So you put the antimatter matter drive down here. You don't use dilithium chloride, dilithium crystals. That doesn't quite work. It's a hard thing to retain antimatter. Sails work. Sails will lift the sun's radiation, will push you out. And then you have to use lasers from Earth to assist to get it to go higher than this. Because as you go out past Saturn, the sun's energy isn't that big anymore. So these sails are huge too. These are like of the order of 20 kilometers. And they're tiny, they're mylar, they're not very heavy. And you deploy them in space, use the sun, and then you shoot lasers to push it out. That's the story. The thing I'm involved with is even more. This is hollowing out an asteroid. And you sell the material, asteroids have a lot of rare metals like gold, 50 times more gold than the surface of the Earth. They have palladium. They have all kinds of rare things. They won't be rare once you start mining them. So a mining company, there's 2 asteroid mining companies, would mine out an asteroid to sell, and then the center of that would be where the habitat would be. It would be kind of like a Noah's Ark, but you're looking like 200 years into the future if it ever happens. So this is how the concept is that this is the asteroid, this is the inside, it's been hollowed out, and it spins. And this shows gardens and people floating around. And this would be a mission this could go a tenth of the speed of light. So it would be the time these people got to some planet, they wouldn't be humans anymore. They would be out there for 300 or 400 years in getting radiation. That's why they're inside of this. The radiation in intergalactic space is high, cosmic rays. So they would mutate, and you can't have. You bring computers along. In 20 years, the silicon in a computer dies. So you have to be able to mine this for minerals to manufacture. You have to manufacture, bring your own world along and manufacture things. And the bad part about this is that when you get to a planet, you have to slow down so that you have to turn it around and blast it the other way, and that's not easy too. These are like kind of fun to deal with. This is called Instant Starship Interior, and but it's mainly to stimulate interest by school children. There's an investment. NASA invested $500,000. That's all they did because Congress would jump on them for the best. As a children education program, which it is. It stimulates children in STEMs. And then you have this is the warp drive kind of concept that you see, science and science fiction. I don't know. This person at NASA, there's one person working at this at NASA. There he is. And he's built a tiny micro hyperspace drive. It's like the size, 2 centimeters, something like that. And I don't know much about it, but this is the movie Interstellar, where they use that for, you use two black holes and you go through your travel like with warp, what the warp drive would do. So the end, how much would it cost to build $3 trillion for humans? And that's a lot of money, and this is for people. But to send a mission out to explore Alpha Centauri, much, much less. You're talking of the order of $100 billion to $200 billion where you send a small mission out. It would take forever, and you have to, unfortunately, you're 4 light years away. We can't communicate, so you have to leave behind little relay systems. So you send the signal out, it hits this system, it forwards it to the mission itself. So you'd have to throw out the back of the craft relay stations to relay the signal back so you can still communicate with it. It's really tricky having those stay in place. They'd have to have propulsion on them to keep them from drifting out of line of sight. So that would be a lot of money. So human in space going to stars is sort of out of the question. But you could get a remote craft that would measure magnetic fields and take close pictures of Alpha Centauri or Proxima Centauri. That's feasible. We have the technology now to go 10% the speed of light without doing anything. We have it, and you have to survive this trip. So you have 50 years to the nearest star, and if you want to go further to where there's really planets, you're dealing with 220-year, 300-year trips, which would mean an asteroid maybe isn't a bad idea. because you would have mineral resources. Some asteroids have water in them, so you'd have to pick the right asteroid. And the end of this is, what's the case for it? Is this distant future? First, Mars colony is a no-brainer. I think that's a good idea because Mars has the resources. It's not far away. You could create new space economies like mining is being done. And then this is the quote from the president or vice president of Icarus. Through reaching out for the stars, humanity will incite a new era of thought and capabilities. This is sort of wishful thinking, with potential to transform our culture and technology, to heal the Earth and enrich human experience. It's sort of like a Star Trek kind of theme. The easiest way is maybe try to find communication. Is that intercept a signal, send signals, and do it the easy way by radio communication. And that's it. Thank you.